Okay, so in this second part for Fatou's lemma, Fatou's lemma, what I want to do is the second case. So the second case, remember, case 2, is that this integral here is finite. And so remember, in general, we're showing that this integral here is less than or equal to the lim inf as n goes to infinity, and if this is true on E. And this is simple. This is a simple function. So we did the case, the integral of var phi is infinite. Sorry, brain fart there. Yeah, so we did the case where the integral is infinite. In that case, we showed that the limit on the right-hand side is infinity also, which means the lim inf is infinity. So, or rather, the limit as n goes to infinity of the integral of the fn's is infinite, which is the same thing as saying the lim inf as n goes to infinity is infinite. So yeah, this is simple. Okay, so yeah. So how do we handle this case, which is definitely a little more complicated? It's a somewhat similar, quite clever argument that we're going to use. Okay. Right. Okay, so yeah, we're assuming this. So clearly this is finite. Oh, okay. So what I need to do first is excise the 0 set. So in particular, let E0 be the inverse image of 0. So a set of all x and e where the var phi, my simple function, is 0. Okay, and if I do that, and let's say e prime is e take away E0, well, clearly this also is finite. And this equals whoops, sorry. So this is finite, and this is going to be equal to E prime. Well, E is E prime union E0. Okay, well, my function is 0. On E0. In particular, the integral over E prime is also finite, and my function is positive on E prime. It's a simple function on E prime. Positive simple function on E prime. Okay. All right, so let's say epsilon is positive. And let me set this here to be y1 through, for lack of anything better to use, let's say YL, or some natural number L. And here everything is positive. Because we've excised the zero set. So additionally, set M to be the max, big M to be the max of all these. And let's set epsilon prime to be epsilon over M plus this integral. Okay, which is well, it's positive. The denominator is positive. Everything's finite, it's a real number. So yeah. Okay, so yeah, so kind of like we did before, a little harder to even motivate why we're doing this, but we'll see in a minute. It's a really clever argument here. Not very difficult, but very clever. So here I want to use continuity of measure going the other way. In particular, what I mean is I want to get nested sets and use continuity of measure. All right. So yeah, let's say En is a set of all x and E prime, where Fk of x is less than or equal to 1 minus epsilon prime times phi of x, or var phi of x, whatever it is, for some k bigger or equal to n. All right, so something to note that I'll use in a second. Clearly, this being infinity implies this integral is infinity. In particular, the integral is bigger or equal to the minimum of all these. Times this measure. So that means this, and remember this is positive because all the y's are positive. That means this has to have finite measure. In particular, why do I care? Well, in particular, E1 is a subset of E prime, and so E1 has finite measure. And I should point out, we'll use this in a little bit. We don't really need it now, but let me not use purple. It doesn't it blends in too much. I'll use yellow here. So you can actually, I mean, trivially you can write, or not trivially, but very easily you can write this is going to be k equals n to infinity. And in this case, it's clearly nested. These sets are getting smaller and smaller and smaller. And again, I'm just writing this to indicate why it's clear that these are nested sets. They're getting smaller and smaller and smaller. But we will use this, what's in the yellow, in a minute. And in a little bit. So Okay, so by continuity of measure, we have the limit is the measure of the intersection. Okay. Now I claim, the limit is 0, and I'm going to prove the limit is 0 by proving that this is empty. Okay, well, let's see why this is true. If X is in this intersection, and I'll leave some 511 details for you to do. So first, well, first of all, X, if X is in this intersection, that's an E prime. So this, not stating a whole lot here. We're at E prime, so this is positive. This is a simple function less than or equal to f of X. This is the limit. And the point here is if we're in all of the ENs, then no matter how far into the sequence we are, we can always find a large K where Fk of X is less than or equal to 1 minus epsilon prime phi of X. Or rather, for any N whatsoever, we can always find a K bigger or equal to N where Fk of X is less than or equal to 1 minus epsilon prime phi of X. So that means this is less than or equal to 1 minus epsilon prime. I'm going to do that. Phi of X. Again, if you have any doubts, prove this. This is where we're using X as in the intersection. Again, what are we saying? What does it mean to be an intersection? For any N whatsoever, we can find a K larger where Fk of X is less than or equal to 1 minus epsilon prime phi of X. Okay. And because the limit as K goes to infinity is equal to f of X, there's a little easy basic analysis argument says this is true. Okay. If you have any doubts, I would prove it yourself. Okay, but this is absurd if you think about it. Why? That's kind of the point. We're trying to prove that this is empty. Right. So in particular, let me divide by, well, I'll just write this out. So let me divide out by phi of X, and I will second. Yeah, sorry. For some reason I thought I had 0 here when I divide out. So what does that mean? 1 is less than or equal to 1 minus epsilon prime. So minus epsilon prime, or rather 0, is less than or equal to. This is clearly absurd. 0 is less than or equal to minus epsilon prime. This is absurd. So in other words, saying picking X in this intersection gives us a contradiction. Okay, and again, why do I care? I want this limit to be 0. Right, and by continuity of measure, the limit is the measure of the intersection, which is the measure of the empty set, which is 0. So we get the limit is 0. Okay, so we're actually almost done. Pick big N. Where little n bigger or equal to big N gives me that the measure En is less than epsilon prime. Okay, so now I want to look at the complement of En. Remember, we had En is this union here that allows me to complement it complements very easily. Sorry, it's the union, not the intersection. It's the union. Yeah, so take the complement in E prime. This is going to be the intersection. So it's the intersection of these complements. So if it's not less than or equal to, it is bigger than. As simple as that. Okay. And in particular, well, X and E prime take away E N implies F. Well, in particular, this says that X is in the K equals yeah, sorry. X is in the K equals N set because N is bigger or equal to N. This is the intersection where K, is N plus 1, N plus 2, etc. So in particular, K equals N is part of the intersection. So Fn of X, this is really crucial. Okay, so this in green. So I'm going to need this, and I'm going to need this. And I also need this, but it's a little less, it's much more trivial than the other ones. So I need those 3 facts in green in a minute. I'll go back in a second. Okay, so yeah, what's my original goal? Need to get a lower bound on these integrals. That's kind of the goal. So this here, bigger or equal to integrating over E prime, take away E n. Okay, on E prime take away E n, this is true. So this is bigger than, or bigger or equal to, doesn't matter. 1 minus epsilon prime times the integral of 1 minus, sorry, integral of the simple function, bar phi. Okay, now I'm going to write it as integral over e prime minus the integral over en. Okay, yeah, so okay, 1 second. To check something really quickly. Bear with me a second. Yeah. Okay, so this is equal to this integral minus this integral here. Right, but this here, of course, is less than 1. Okay, so this is going to be bigger or equal to, because this is less than 1. So the whole thing without the minus is less than the integral of en fn. Minus makes it bigger or equal to. Okay, and this whole thing here is going to be less than or equal to m times the measure of en. So they should be the simple function, not fn. I don't know why I wrote that. Sorry about that. Right, so remember the simple function is less than or equal to m. Because m is the max of the range of the simple function on e prime. Yeah, so so it's less than or equal to m times the measure of en. And that is less than or equal to well, m e prime minus, so it's bigger or equal to. So what is this equal? This is going to be equal to phi of r phi, whatever. Integral of r phi minus epsilon prime m plus this integral. And this is bigger or equal to, remember, epsilon prime was set to be epsilon over yeah, this is what epsilon prime was set to be. So this is going to be integral phi minus epsilon. Again, epsilon prime was set to be epsilon over this whole thing here, which is right here. So less than that minus makes it bigger equal to. Okay, so what is the conclusion? Little n bigger than big N implies the integral E n is bigger or equal to integral E prime phi minus epsilon. Okay. So in other words, this here, what I'm going to circle in whatever color this is going to be a lower bound for all of these integrals for n bigger or equal to big N. That's the point. The inf is the greatest lower bound. So this inf is bigger or equal to this integral here. Okay. Right. So, but so as n goes to infinity, big N goes to infinity. We're taking the infimum over less and less and less indexes, less and less and less integers. So the infimum increases because it's we're looking at less and less and less stuff. We're looking at less and less and less of these integrals as big N goes to infinity. So in other words, as a function of big N, so I'll write it like this. Just repeating like a basic fact of really limits. So sorry, this is increasing. This is increasing. So in particular, the lim inf I'll use n little n. So this is bigger or equal to this inf here, which we concluded is bigger or equal to e prime minus epsilon. Yeah. Here again, we use that the inf is the greatest lower bound. All these integrals for n bigger or equal to big N. All right. Yeah, and epsilon is arbitrary. And actually, really, these integrals, this could be infinity. We don't care at all. It's increasing. There's a subset of non-negative numbers. Well, of course, remember E prime is simply E with the zero set excised. So this was arbitrary. We get exactly what we want. The lim. So again, not a hard proof, but like a really, really clever proof. I definitely would not be able to just sit down and kind of think to my piece out, flesh out like the way the idea to prove this. I would not think of doing it this way in a million years. It's really clever proof. Yeah, a long proof, but yeah, hopefully it's made sense. If not, just let me know. And yeah, that's that. All right, so long, take care. Bye-bye.